got it too. So covalent bonding, as you told me, is the sharing of electrons. For example, you can see in ammonia that a covalent bond formed between two atoms when an atomic orbital containing a single electron from one atom overlaps with another atomic orbital, which also contains a single electron of another atom. Now, the two electrons in the area of overlap are the bonding electrons, and they are sometimes referred to as the shared pair of electrons. This is a bond pair, bond pair, bond pair, and then we have a lone pair, which is not bonding. Atomic orbitals can be any of those found in the atoms. It depends that what orbital was the outermost shell of. It's, let's say, one of the electronic configuration was 1s2, 2s2, 2p5. Then its outermost orbital is a p1, like this. And let's say if the other
Yeah.
one was 1s2, 2s1, then the outermost one
It
was
would be
s.
like the first one.
तो आपके पास sp बॉन्ड भी बन सकता है, ss भी बन सकता है, pp भी बन सकता है, and these are all the different types. When
Is it
ss
a F?
bond, it forms a sigma bond. We write it like this. When p orbitals bond together, pp and pp, there are two ways they can bond. Head-on collision. Head-on collision अगर होगी, it's also going to form a sigma bond. लेकिन अगर sideways overlap होगा, it is going to form a pi
Pi
bond.
bond.
End-to-end overlap leads to the formation of a sigma bonds, and this leads to the formation of a single bond between the two atoms. A sideways overlap of two orbital, p orbital, leads to the formation of pi bond, and a feature of pi bond is that it cannot form until a sigma bond has been formed. For this reason, pi bonds only exist between atoms which are joined by double or triple bond. Any atom, any compound which has a single bond contains only sigma. One of them, if it has a double bond, it contains one sigma, one pi. And if there's a triple bond, for example, nitrogen के अंदर, it's what? Sigma pi pi. For
Yeah.
example, hydrogen को आप देखिए, this is how hydrogen का एक dot and cross diagram कैसे बनती है, where two s orbitals overlap to form the new
Yep.
molecule. Both hydrogens are 1s1, 1s1. So उनमें
No
ss overlap
sigma.
होगा exactly. अब क्लोरीन को देखो, क्लोरीन इज 1s2, 2s2, 2p6, 3s2, 3p5 है, तो यहाँ भी p है, दूसरा क्लोरीन भी 2p5 है, ये भी 2p5 है.
So we will also be sigma.
एग्जैक्टली. फिर पाई बॉन्ड फॉर्मेशन कहाँ बन सकती है? इन लेट्स से नाइट्रोजन जैसे ट्रिपल बॉन्ड है, दिस आल्सो नीड्स
Yeah.
5, दिस नाइट्रोजन आल्सो नीड्स 5, दे बॉन्ड 3 इलेक्ट्रॉन्स, तीन पेयर इनके दरमियान में बनते हैं,
So
एंड
then
दे
it will be
फॉर्म अ
5
ट्रिपल
and it's
बॉन्ड टू
3.
बिकम N2.
Yep.
Over there in N2, now one of them would be sigma, the second bond would be pi, and the third bond would also be a pi. तो आपके पास दो देखो sideways overlap हुए हैं, pi pi, and the middle one is a sigma. Got it?
Yep.
Bond length and bond strength. Remember, greater the bond length, lesser would be the bond energy. The bond length is the distance between the nuclei of the two atoms that are covalently bonded together. The strength of a covalent bond is measured in terms of the amount of energy required to break 1 mole of one bond in gaseous state. And here you can see that as the bond length is actually decreasing, okay, what is happening? The bond strength is increasing in some cases as well. So the general
Yeah.
relationship between bond length and bond strength is that for the bonds that are of a similar nature, shorter the bond, greater the bond strength. This is a result of an increased electrostatic attraction between the nuclei and the electrons in the overlapping atomic orbitals. So bond length is the distance between the nuclei of the two atoms that are covalently bonded together. Got it?
Yep.
Good. Let me show you one thing.
Introducing the English test designed for you. Convenient, fast.
Hi, it's Mr. Anderson, and this is Chemistry Essentials Video 52. It's on bond length and bond energy. Some of the first bond lengths ever measured were measured by scientist Kathleen Lonsdale, who was an X-ray crystallographer. She would put a solid crystal in front of X-rays, measure the diffraction. It told her a lot about the structure of that molecule, and she could even measure the distance between atoms. And that allowed her to unlock the structure of hexamethylbenzene, that famous benzene ring. She was able to determine that it was a hexagon, that it was flat, And she even measured the aromatic bonds. In other words, the single double bonds between the carbons. And by measuring the length of that eventually led to this whole idea of resonance. So not only was she an amazing chemist, but she broke down a lot of walls. She was one of the first 2 females fellows elected to the Royal Society, first tenured professor. She was an amazing scientist, but she really got us down this road of bond length and bond energy. And so if we have 2 atoms, they're both going to be attracted to one another. And where does that attraction come from? It's the electrons of one atom being attracted to the protons of another. And so that's going to pull atoms together. But if they get too close to one another, then there's going to be repulsion. And we can measure these forces just using an energy distance graph, where we've got the energy that's pulling those or pushing those apart, and then how far they are physically separated. And using a graph like that, we're able to determine the bond energy, the energy holding them together, and also measure the bond length, how far those atoms are going to be apart. And so the bond energy, if we were to define it, is simply the energy required to break those atoms apart. Now likewise, when we form a bond between the two, we're going to release energy, and that's just simply the negative bond energy. Now the strength of that bond, or the bond strength, is going to be built upon the charges of the atoms themselves. The bigger the charges are, the greater that bond energy is going to be. And as we increase the number of electrons in a bond, so as we move from a single to a double to a triple bond, we're actually increasing the charges and therefore increasing that bond strength. And one interesting thing that you should know is that as we increase that strength, we're going to pull those atoms together and we're going to actually decrease the bond length. And so if we look at these 2 representative atoms right here, as we bring them close together, there's going to be attraction. In other words, as we shorten the distance between the atoms, as they get closer and closer together, there's going to be a greater attractive force. Now, as they start to get really close together, there's actually going to be repulsion between those 2 atoms that's going to push them apart. And so we can find what's called that Goldilocks, the point where they're not too close, not too far away, and we're going to have the highest amount of energy right here. And they're just going to kind of vibrate at that space. So if we were to look at 2 atoms, like 2 atoms of hydrogen, we would find that energy to distance graph would look something like this. There's going to be attractive force between these 2 hydrogen atoms out here, but as we bring them closer and closer together, that energy of attraction is going to get greater. As we move them even closer, then we're going to move into this whole idea of repulsion. And so this is going to be that Goldilocks area right here. And so what we can measure then is the bond energy, the energy holding those atoms together. And likewise, since we've got distance here on the x-axis, we can measure the bond length, how far those atoms are apart. And so if we define what is bond energy, it's just 2 atoms connected together. And so bond energy is the energy absorbed when we break those atoms apart. Now likewise, there's going to be energy that's released as we bond those together, and that's going to be the negative bond energy. It's going to be exactly the same. The amount of energy to break it apart is the same amount of energy that we get when those 2 atoms are going to be attracted together. Now what contributes to that bond energy? It's going to be the electronegativity of all the atoms involved in that molecule. And so let's say we were to look at boron. Boron is going to have an atomic radius of 83 picometers. What does that mean? The distance from the center of that nucleus to the outside is going to be 83 picometers. And so if we were to connect a boron to a boron, we would anticipate that that bond length, the distance between the 2 atoms, is going to be twice that. It's going to be 166 picometers. But if we were to measure the actual bond length in a molecule, let's throw one up here, and it ends up being 175 picometers. In other words, they're farther apart than we would expect. That means that we're going to have a very weak bond between these 2 atoms. And so basically, as we increase that bond length, that distance between the atoms, we're decreasing the bond strength. Now, if we were to use another example, let's say we're looking at rhenium, which has a radius of 137.5. If we had 2 rhenium atoms, we would expect that that bond length is going to be 275 picometers. If we actually measure it in a molecule like this, and it's less than that, that means that they're really overlapping. There's greater charges holding it together, and so we would call that a strong bond. Again, the higher your bond energy is, the closer those atoms are going to be, and the shorter that bond bond length is going to be. Now, what happens as we increase the bond number? Let's say we're looking at two molecules that look essentially the same. We've got ethane, which is carbon attached to carbon and then hydrogen around the outside, and then acetylene. And so this is the same thing, carbon attached to carbon with hydrogen around the outside, but in this case we've got a triple bond right here. How is that going to affect the bond strength and the bond length? And so if we look at these two carbons, we've got one that's a single bond and one that's a triple bond. If we were to measure their bond length, we would find that as we increase the number of bonds, we're actually decreasing that bond length. They're getting closer and closer together. Well, what does that tell us about the bond energy? The bond energy is increasing over time. So again, the more electrons that we're sharing, the more charges there are, the greater that bond energy, and therefore the shorter the bond length is. If we were to measure the same thing with nitrogen, single, double, triple bond, we'd find that we're decreasing the bond length again. So what's going to happen to our bond energy over here? It's going to increase over time. And so did you learn to describe the energies involved in both breaking and forming chemical bonds? I hope so, and I hope that was helpful.
All right. Is that mentioned bond length and bond energy clear?
Yeah.
All right, good.